Alright, so this is a video on using Spider to produce the eigenface example. And so you might go ahead and download the Spider or the eigenface example in Python that's either available on our class website, or you could just read along in the notes. Alright, so the first part of this is going to be basically just importing the things that we need. And notice that I wanted to draw your attention to line 17, right? Because mat contents. This is the load mat command from the SciPy.io package, and this allows you to read in a MATLAB data package, and so that's really nice. And then the next few lines are how you extract the variables from that binary file. And so you see here we have faces. That's the matrix of photographs. We'll take a look to see what the size is of that. M and N are the sizes of the length and width of the image. We have another image. It's the image of a dog, and we're going to take a look at that for some reason. I'll keep it a secret for now. And then finally, there's this vector n faces that we'll take a look at. Okay, so let's go ahead and see if we can run the cell here. I'm still getting acquainted here with our Python. Let's run the cell. Good. And now we can take a look at our variables. Good. And so you see that faces is 32,256 by 2410. So that's 2,410 faces. Each is 168 by 192. And so if you multiply those together, you get 32,256. Okay, and so when we're creating an image, we have to convert this vector back into a 168 by 192 matrix, right? Good. So we'll keep that in mind. The n faces here is something else here. You'll see 64, 62, 64. What's happening is that the data set consists of 38 people's photos. So how do you get to 2410? Well, each person has approximately 64 poses. But you'll see here that some people have 64, some people have 62. So n faces is telling you how many poses that particular person has in the database. Okay, so the first person has 64, the next person has 62, the third person has 64, and so on. And they're all ordered, which is nice. It makes it easier to figure out who's who in your database. Okay, so why are there 64 images per person? Well, what they did is they changed the illumination on the face a bunch of times, so you get a good kind of record of how the illumination hits that face. And so if you look in the notes, you'll see an example of the first person. I think I plotted the first 36 out of the 64 images, and so you can kind of see how the illumination varies per photo. Okay, so that's what the data set is. Now we've got the data all set up from MATLAB, and so now we're ready to go ahead and work our magic here. So first of all, we're going to, out of this 38 person data set, we're going to just use the first 36 people for training, so-called training the eigenfaces, the set of basis vectors for this space. And then what we're going to do is we're going to see how well our basis works with photographs that we have not trained on yet. Did you get that? So we're going to leave two people's photos out of the set, and then we're going to find the SVD, or the best basis, using the SVD, and then we're going to perform a partial projection of unknown faces into our subspace and see if they're well represented there. Okay, and so by the way, that's what we're going to be doing with the face of a dog. Do you think the subspace is going to represent a dog's face very well? That's an interesting question. So, okay, so the next cell here, we're just loading up our data. So we'll go ahead and run that. Good. And so now we have training faces. And again, that's 2282. So that's, you can kind of see what the numbers represent there. But this is the first 36 people. Good. So now, what do we do first with our data? Now that we have our training, you always mean subtract. So that's what's happening in the next cell. We take our average face, which will be the mean, and then we take our training faces minus the average face. Notice that in Python I had to do a little reworking here, and that's because of the MATLAB to Python interface. It changed a little bit, so yeah, so we have to do a little bit of manipulation there. That's okay. So this is how you take the mean subtract. This is how you mean subtract the mean from the columns of your matrix. Good. So it's just that simple. And so next we set up a figure, and now we're going to, this is our command on line 34, where we're showing you the average face, and notice that it's being reconstructed, right, as an m by n, but then it's, for some reason, mshow I think is doing this opposite of what we would normally see as an image, so it's transposing that. Okay, then it's setting the color map to gray. We're setting the title to mean face. We're turning the axes off, and then we'll show the result. So you ready to see the mean face of our data? Okay, there it is. So there's the mean face of our data. It's mean. All right, so that's kind of interesting. Let's see, so now all that's left is compute the SVD. And so in the next cell, we're basically done with our constructions process. So let's go ahead and run that because it's going to take a minute. If you watched the MATLAB version of this, you know it takes a moment or two for the computer to do this because the matrix is pretty large. And my computer has a lot of memory, so that tells you how much memory you have to have if you have a really large database. So just to let you know, Washington State was running an Eigenface routine on the driver's license database, driver's license photo database. And so the idea here is that you can do, oops, I guess I'm going to have to stop my story and we'll run the story later. So, well, the idea is that if you project a person's face into the basis representing the space of driver's license photos, then what you're looking for is to see if there's a match, and if there is a match, see if there's multiple matches. And when they started doing this process, they actually found that there were a lot of multiple or duplicate driver's licenses around with some shady names. So there was some comment that maybe the CIA was up to something, but I won't comment on that. Okay, let's get back to our work. By the way, now it's people don't use the Eigenface routine directly anymore. What they do instead is they use PCA on biometrics. It's a little bit harder to fool the algorithm. We might try to fool the algorithm later. Okay, so for the singular values, we just want to plot and see what they look like. So let's take a look. Run that cell. Okay, so here you see the singular values. It's always good to just take a look at them. See what kind of shape you have here. See, it's dropping off dramatically after. We'd have to check to see what the value is. But you can see that clearly there is a cutoff though. So this is a little bit lower dimensional. And of course, another way to check is to try to look for the what am I saying? The normalized eigenvalues of the covariance. So I'm going to pause for a second and we'll take a look at that real quick. Okay, we're back. So I included a few extra lines here, lines 49 and 50. I think this is going to work. I see an error for some reason. Oh, I forgot PLT there. Good. I'm jumping between MATLAB and Python tonight. So, good. Now let's see. Let's go ahead and save that and run this file. Good. Now, what do we have here? Did I forget my PLT show here? I think we're running into multiple images going on. Let's see if I can just show you this last one, because this is the one I wanted to emphasize, because these are the normalized eigenvalues of the covariance matrix, and they have important statistical considerations. Oops. I see I'm using my MATLAB commands. Good. Were you guys yelling at me? That's not Python. That's MATLAB. Okay, let's try this one more time. I think I've got it now. Let's see. This should have. We'll go ahead and put a show here too. Just make sure it all looks good. Oh, I guess I could open up a new figure just to be sure. Okay, how many figures am I going to have open here? A ton of them. Okay, let's go ahead and run this cell now. I think it'll work. Did it work? Oh yes, very good. So this was our logarithm data, and then when we do the normalized eigenvalues, do you understand what you're seeing here? So underneath here is the number of the eigenvalues you need, normalized eigenvalues, in order to capture a certain percentage from 0 to 1 of the variance of the data. And so you can see here that it reaches pretty close to 1 pretty rapidly, right? So before 500 eigenvalues, you can get pretty close to 100% of the variance. So you can see that it takes a lot of vectors, from 500 on to 2000 in order to fill in all the missing information that's in the pictures, to make them sharper and sharper and sharper. Good. So that's an analysis of the singular values. That's important to look at. I'll have to change the text. Maybe I'll just leave it in the actual Python file, and just I'll update the text later. So in the next video, we want to take a look at some eigenfaces. Those are the basis vectors of the covariance matrix. Good. And first four. And so here you see the first four eigenvectors. These are the basis vectors for face space. The first four, 1, 2, 3, 4. And yeah, that's really kind of weird. Interesting to see those. Let's get a little more space here. And down below, it's still the same eigenvectors. However, it's the photographic negative of the ones up here. And do you see why? Because our basis vectors are normalized, and so they're basically have been divided. So there's lots of numbers that are negative and lots of numbers that are positive in these vectors. And so taking the photographic negative, then you could really, the same vector is giving both. And so it's kind of interesting to see how these vectors then reconstruct a face. So for example, you see in this negative value of the first eigenvector, it's really clearly setting up, the major features of a face: the two eyes, nose, mouth. And then the next eigenvector, the positive side is highlighting the right of the face, and the negative is highlighting the left part of the face. So that's kind of fun. This third eigenvector, it looks like it's working on the nose. Third and fourth eigenvectors are working on the nose, it looks like. Something's going on weird with of course this is a photographic negative, right? So that's why it looks like the person is cross-eyed there, even though that when you do the photographic negative, oh wow, you get something pretty bizarre. Okay, so those are fun to look at. Take a look at them at some point. All right, now We want to do our projection now of faces 2 and 7, or people 2 and 7, onto basis vectors 5 and 6, just to see what happens. And so these formulas up here are just ways of getting to those columns in the database. And so remember, person 2 has, I think, 62 poses, and person 7 has somewhere around 64 poses. And so this is about 128 columns of data between person 1 and person 2. It just turned out to be a little bit faster in Python to just go ahead and do them separately, and so that's what you're seeing here. And so let's see what these look like. We're going to project these data points onto the best two-dimensional basis for face space using basis vectors 5 and 6. And there they are. And so you see, it's kind of interesting that something happened in basis 6, right? Because if it's positive, it's more like person 2, and if it's negative, it's more like person 7. And so that's kind of a weird result. I don't think you're going to see that in most of the other dimensions. So the question might be why? Why does that happen? Maybe we'll see that somewhere. Didn't I put that in here? I thought I did. Yeah, it's well, see if you can do that if you're working on Python. See if you can put together a quick little eigenface plot similar to step 7. Let's just go ahead and get to step 7. I don't want to keep you for too long. I've been droning along here. So let's do the eigenface reconstruction of an image that was omitted from the test set. And so the first image here is the original, and so you see that this is the 50 dimensional reconstruction. The next one is 200 dimensional reconstruction, 500 dimensional reconstruction, 1000 dimensions, and 1600 dimensions. And you can see even after 1600, right, there's some shading that still needs to happen, but it's a pretty close match. Actually, after about maybe 1000, 500, something like that. Yeah, the first few you see aren't really getting visually anyway. You can't really tell who it is. It takes a few more dimensions to fill in the missing information. Good. And now at the last one, we're going to try doing the same thing with a dog. Let's see what happens. Ooh, wow. I will let you look at that. So the first image is the original dog, and then as we go across here, this is 50 dimensions, 200 dimensions. That's really bizarre. 500 dimensions, starting to look like more and more like a dog. Then 1000 and 1600. By the time we hit 1600, it's pretty good, right? You could definitely see good similarity there. Okay, so that's pretty amazing because we're only using 1600 dimensions for 32,000 dimensional space, and the dog is nowhere near close to the images of a person. However, you can kind of see how the eigenfaces are kind of being deformed to force the shadows and highlights into the desired shape. Very good. Okay, so play around a little bit with Python code. I think you'll find it kind of interesting to see. All right, I will see you later.